In 1947, something amazing first rolled off a production line in the Soviet Union. Something that would become a widely recognisable symbol of Soviet post-war ingenuity. A product so reliable and so well engineered, many are still in service to this day. And many have been built under licence outside of the Soviet Union, even into the 21st century. This is a system so well conceived it can be maintained by almost anyone with comparatively little training, and spare parts are easy to make or mass produce. It's seen wider use in its field by both the military and civilians than any comparable system, and will no doubt remain in use for decades to come. Of course, I'm talking about the Antonov AN-2. This video is not about the AN-2. It's about its idiot child, the PZL M-15. First of all, before anyone panics, the video that's going to be featuring the Antonov AN-225, that is coming up next. I promised it at the end of the last video. I wasn't anticipating crossing 100,000 subscribers before then, so we get this 100k special first, and then I'll be back in a month or so with that video. This channel blew up due to an engineering train wreck, so what better than to do a special video on another one? Unlike some of the depressing engineering disasters I've covered in the past, this one is, well, it's all just a bit silly. Now, this video wouldn't have been possible without one of my patrons, Shirakami, who went over to the Polish Aviation Museum near Krakow to film some fantastic footage of their PZL M-15. He then went and translated a bunch of Polish sources into English for me. Oh, and I forgot to mention, it was him that came up for the idea for this video in the first place. So huge thank you there. We have to make things clear at the start, mainly to prevent any of my Polish friends from killing me. The PZL M-15 was designed and built in Poland. It was designed to meet an absolutely ridiculous set of requirements which called for an uneconomical, impractical, and generally all-out embarrassing aircraft. And those requirements came from an entirely different country. Can you guess which country it was? It's pretty obvious, right? The Poles have decades of good aircraft design and engineering culture in general. It's just that the M-15 was built during their weird communist phase. And finally, I've decided we're not going to be complete saddos during this video. The M-15 was a biplane, but technically because one wing was smaller than the other, it should be called a sesquiplane. That sounds daft, so it's just a biplane for this video. Apparently the correct term for a crop duster is an aerial applicator. Let's just stick with crop duster, shall we? I'll put a note on screen if there are any more of these pedantic details that I've simplified. Okay, so which country was really behind this jaunty aircraft? Absolutely no prizes for guessing. Well, obviously it was the Soviet Union. 200 engineers were involved in the creation of this aircraft. And with the terrible leadership of two communist countries, we truly have an aircraft designed by committee. Okay, so I figure I get to do one Soviet anthem drop per subscriber milestone. Anyway, this story starts, and to be honest kind of ends, with the AN-2. It's difficult to deny that the AN-2 is one of the greatest aircraft of all time. It can be used to transport cargo or passengers, both military and civilian. Variants have been built for water bombing, as seaplanes, for airborne research and ambulances. It can land virtually anywhere. It's easy to fly and has excellent pilot visibility. And these factors made it uniquely suitable for a different application, crop dusting. A 2-ton hopper can be installed in the fuselage to spray crops with chemicals, and the Soviet Union had plenty of crops to spray. Though large for a crop duster, the comparatively high payload capacity and stability of the AN-2 made it ideal for extended work spraying the expansive farms of Russia. And interestingly, the majority of them were built in Poland by the state-owned manufacturer WSK Mielec, subsequently PZL Mielec, the heroes of today's video. But by the 1970s, the AN2 was beginning to show its age. There was nothing wrong with it, but to keep feeding the Union, surely something more current than a biplane powered by a radial engine was necessary. The Poles agreed. Mielec had tentatively begun an attempt to rejuvenate the country's aviation industry by commencing work on the M-14. This would replace the crop dusting duties of the AN2. It was to be a huge aircraft for its class with a 20-metre wingspan and powered by a 1,250 horsepower turboprop engine. Those wings would require bracing, and we'll talk more about that later. But crucially, on paper, there's no reason to assume this wouldn't be a great aircraft for the role. It looks like a crop duster, just a really big one. We're going to gradually find out why crop dusters look that way. But now it's time for the Soviet Union to enter the picture. And thanks to them, the world was eventually graced with a jet-powered fixed undercarriage biplane crop duster. Now, it would be easy for me to spend the next 40 minutes mocking this, but I'm not going to do that. Well, I'm not going to do that exclusively. You see, I think there was some method to this madness. Let's not kid ourselves, the M-15 was an absolutely ridiculous aircraft that was ill-suited for, well, anything really. But with some changes, I think there could have been a good aircraft in there somewhere. So let's examine all the major wacky design choices, find out why they ended up in the design requirements, and figure out what on earth the Soviets were thinking. I think it's best to start with what must have been the worst design choice of all. A jet engine in a crop duster. There are many reasons this only happened once, and we'll go through those reasons in this chapter. The engine chosen was the AI-25 medium bypass turbofan, prominently used on the Yak-40. By all accounts, a perfectly respectable engine. A derivative of it was even used recently and prominently on the Turkish Bayraktar drones. You'll note a Bayraktar and a Yak-40 are less aerodynamically challenged than an M-15. So let's talk about fuel efficiency. You've probably heard before, jet engines, specifically turbofans, are extremely efficient, but there are different types of efficiency. Where a typical internal combustion engine will convert something around 25% of the chemical energy in the fuel to motion, a turbofan manages closer to 65%. Now, a propeller cannot accelerate incoming air to as high a speed as a jet engine can. So for two broadly equivalent engines, the jet is more efficient at accelerating air. But see what I did there? I'm talking about engines just sat on the ground and not moving. All of that newly converted kinetic energy is in the air, which flows at high speed out of the engine exhaust. So I was talking about the efficiency of just the engine itself. We really only care about how much kinetic energy goes into the vehicle itself. This is what I'm talking about when I refer to fuel efficiency. How much chemical energy in the fuel is eventually converted into kinetic energy of the aircraft. This is also referred to as the propulsive efficiency of the aircraft. Now, if you try Googling why propellers are more efficient at low speed, you'll get a ton of overly detailed descriptions of bypass air, high combustion temperatures, propeller tip speed limitations, and much more info we do not need. Here's how I've always thought of it. We don't care how the engines work, we just know that a jet accelerates air to a higher speed than a propeller. So let's put a propeller aircraft on the runway, turn on the brakes, and spin up the engine to full power. All the energy is currently going into that backward airflow and none into the vehicle. The propulsive efficiency is 0. Okay, now let's just take off and get up to cruise speed. The cruise speed is relatively low, but so is the rearward airflow. From the perspective of a stationary observer, the forward airspeed of the aircraft is subtracted from the rearward airflow, so only a minority proportion of the kinetic energy from the engine is used to accelerate air. The majority of that energy is now used to accelerate the aircraft. In an ideal hypothetical case, the rearward airflow would be 0 relative to a stationary observer. That would give 100% propulsive efficiency because all of the energy had gone into the aircraft. Now let's take a jet aircraft and fly it at cruise speed. The rearward airflow is significantly faster, so to prevent all of our kinetic energy going into that airflow, we designed the aircraft itself to fly faster. This is why jet aircraft fly at a higher altitude where air resistance is lower. Remember, air resistance increases with the square of the speed. And this is why they're almost universally designed to be streamlined. Minimizing that air resistance is crucial to ensuring our fuel is used to accelerate the aircraft, not the air. With all that in mind, let's do something ridiculous. Of course, no one would actually build an aircraft like this. We'll increase the drag as much as possible by making a huge frontal area. I don't know, let's just replicate the fuselage a couple of times. And let's be really funny by adding a second wing with a huge twin tail. And while we're at it, we'll make the landing gear non-retractable. Now let's fly this extremely silly aircraft as low to the ground as physically possible where the air is at its most dense. Now, our jet engine is only going to be able to get the aircraft up to a relatively slow speed before it can't overcome the air drag. The problem is, that exhaust is still moving at the same speed relative to the aircraft that it was before. The end result is us accelerating a lot of air backwards at a high speed, whilst accelerating not very much aircraft forward at a low speed. Most of our fuel is being used to accelerate air, not aircraft. Now, maybe we could combine the high combustion efficiency of a gas turbine with the propulsive efficiency of a propeller at low speed by connecting the two via a gearbox. Oh, right, yeah, that's just a turboprop. I wonder how many times I'm going to say they should have just used a turboprop in this video. The AN2 was not considered particularly fuel efficient at the time. It consumed about 200 litres of fuel per hour. For the M-15, it was 550 litres per hour. Hilarious, considering the AN2 had a higher cruising speed. Now, there is a theory that because jet fuel was, quote, cheaper than gasoline in the Soviet Union, end quote, that made sense economically. I absolutely do not buy this at all. Jet fuel is certainly cheaper than the more refined avgas used in piston aircraft today. I think it being less than 35% of the price would be pushing it, however. And, you know, turboprops ran on jet fuel. Just use a turboprop. There are a couple of other weak arguments for using a jet engine. I don't buy those either. One would be the leniency of jet engines when it comes to that fuel. That is why jet fuel is less refined than avgas. The gas turbines on the oil platforms I used to work on could be fueled with practically anything. In an emergency, they could even run on unrefined crude oil, but that was very much not recommended and would require a full strip down if it was actually ever performed. I'm going to go out on a limb here and assume that running an aircraft engine on incorrectly refined fuel is very much frowned upon. So no, I don't think it was intended for Ivan to run his M-15 on vodka from the potato farm. Jet engines are incredibly reliable, as they, in a sense, only really have one moving part. But that does not mean they have less of a maintenance overhead. Due to the high temperatures, stresses, and rated materials, they require specialised inspection and testing. So, while a radial engine may break more often, fixing it can sometimes be done in the field and with much more limited training than for a jet. For similar reasons, flying one requires additional training and certification, increasing the overall cost per hour of operation. Oh, and jet engines are really noisy. That's how the M-15 got its nickname, Belphegor. Though that story is actually quite cool. When exhibited at the Paris Air Show, a journalist used the term in a derogatory manner. Mielec went with it and adopted Belphegor as the unofficial nickname. So, how on earth did 200 engineers manage to be coerced into using a jet engine? Well, the original design, the M14 we discussed earlier, was to be powered by a nice normal turboprop. But as design proceeded, it turned out the intended engine, the GTD-10A, would not go into mass production as its intended primary aircraft, the BE-30, was cancelled. You'd think finding another suitable turboprop would be relatively simple. But no, it seems some weird politics happened, and when 1971 rolled around, that was the point the Soviets decided to partner with the Poles. And part of the agreement was the development and production of, quote, new aviation technologies in Poland, end quote. I've heard it banded around that the Soviets wanted to showcase their tech to the world. Maybe this was part of the reason they insisted on using a jet engine, technology which had already been widespread for 25 years at that point. But either way, I'm pretty sure the actual reason for the choice was just the usual combination of terrible decision-making, corruption, and coercion by higher-ups in two dictatorships. To their credit, Mielec didn't just go straight from an AN-2 to a jet-powered crop duster. They built a test aircraft first, and I'm rather fond of it, so it gets a short chapter of its own. How do you test the feasibility of powering a large biplane with a jet? You ideally want something that can take off with a more conventional engine and switch to jet power mid-flight. Here's what you do. Take an AN-2 and cut the back end off. Put your jet engine in the rear of the remaining fuselage and add the air intake around the side next to where the co-pilot normally sits. Okay, now we can't just add the new fuselage back in again since that's where our jet exhaust is. So build a truss to hold the new empennage and make that empennage consist of twin vertical stabilizers so the jet exhaust can still flow unimpeded. Add tricycle landing gear and new hatches for the pilots to get in and out, and there you go. The La-La-1, short for Flying Laboratory 1. Now, this looks weird, but I'm all for it. The La-La-1 was solely a one-off test aircraft and was designed to investigate the feasibility of the concept. Admittedly, using a jet engine was not really a concept that needed further investigation, but nevertheless, you'd think that flying this would get the idea out of everyone's system. I think the best appraisal of the La-La-1 is given in the paper NASA wrote about it when they became privy to the study. There are a few interesting key details. First, the La-La-1 went from initial concept to first flight in just 8 months, and 2 months later, the first flight under jet power was carried out. NASA referred to this as, quote, an engineering and organisational success, end quote, and I am certainly not disagreeing with them there. The AI-25 jet engine requires a smaller starter engine to spin up. Normally this would be part of the ground support equipment. So how was the La-La-1's jet engine started up mid-flight? It technically had 3 engines, because the starter was also mounted internally. When the time came, a dedicated fuel supply was used to turn on the starter engine, which spun up the jet engine, allowing for the forward radial engine to be cut off. Pilot safety was surprisingly well accounted for something so disjointed looking. All 3 engines were isolated in independent fireproof compartments and had their own fire suppression systems. Egress hatches were fitted in the upper canopy in addition to the new doors which were necessary since pilots could no longer enter from the rear. That's the reason for this ladder as well. In fact, seatbelts were even fitted. Yeah, I can't decide whether NASA were being sarcastic mentioning that, but they state that the base AN-2 didn't even have seatbelts for the pilot. That can't be true, can it? So, what did Mielec learn from the La-La-1? Well, it was fitted with a chemical hopper and dispersion system, and they learnt that jet exhaust doesn't really interfere with the chemical dispersal. It would interfere even less if it was mounted high up. This may be the only tangible benefit of using a jet engine in a crop duster, though every other crop duster on Earth that does not have a jet engine seems to manage this just fine. They also proposed 303 potential improvements that could be applied to the M-15. Because yes, there was no turning back now. The improvements were used to make the first prototype of the M-15, which would go on to have a full production run. Alright, hear me out here. I don't actually think the decision to build a biplane was terrible. I'm probably going to use a Cessna Caravan as a demo multiple times in this video, That's because it's about the only single-engined aircraft I can think of that is of comparable size and purpose to something like an AN2. Caravan uses a turboprop, by the way. Now, there are different approaches to building a rugged aircraft of this size. But back in the 1970s, I think the general approach was to go for a braced high wing. The material science was not quite where we are today, so the bracing allows for a wing that doesn't have to resist excessive bending loads. As crop dusters are designed to carry a payload, the high wing improves stability by ensuring the centre of lift is above the centre of gravity. An advantage over the braced low wing design I mentioned earlier, that would require additional work to ensure it was stable. As I understand it, high wing designs back then were also a little easier to maintain due to easier access to the control surfaces. But high wing aircraft are not suitable as crop dusters on their own. The chemicals they disperse are often corrosive, so deploying them from a boom on a high wing would increase the amount that's blown into the fuselage, degrading it over time and shortening the aircraft lifespan. If we wanted to use an aircraft like this as a crop duster, yeah, we'd have to fit a spray boom. But if we're fitting a boom, we may as well make it an aerofoil to increase the lift. And with that increased lift, we can probably shorten the length of the upper wing too. Replace the brace with a torsion box, which I'll discuss in the next chapter, and there we go, we have a biplane. Completely obsolete for almost every application today, but if you want a slow, stable aircraft with basic material requirements, this could actually work. Let's see what an engineer working for Mielec at the time had to say about it in this translated paper. Quote, "Using a sesquiplane system permitted rational division of the upper and lower wing." End quote. Indeed, most of the lift came from the upper wing, which was also fitted with the ailerons, flaps and slats, the latter of which were designed to decrease takeoff distance. The lower wing had integrated pneumatic pipes to deliver compressed air and to distribute the chemicals to the nozzles placed along the trailing edge. So we could say the upper wing was for lift, the lower wing was for crop dusting in a sense. One interesting point of note, some articles describe the lower wing as being made of laminate. I can't find any evidence for this from original sources. The paper above states that the primary materials for the M-15 were aluminum, steel and glass. Wood is one of the materials that was completely ruled out. So, if the lower wing was made of a laminate, it wasn't a wood laminate. All that said, the paper does describe the ailerons as laminated, whatever that means. The entire airframe was, however, covered with an enamelled epoxy to protect it from chemical corrosion. Alright, so I've discussed the positives of going with a biplane for a crop duster. The problem is, another design choice essentially removed the main advantage of a biplane. In fact, I'm honestly not even sure it can be called a biplane anymore based on what I'm about to discuss. So, why were most early aircraft biplanes anyway? See if you can guess what flavour of engineering my degree is based on how I explain this. Okay, let's take something like that braced high-wing monoplane from earlier. I'm going to do some unspeakable things to it, so, well, brace yourself. Removing the bracing would put an awful lot of bending load on the wing roots here. Even with the bracing, the bending load is significant. During the early 20th century, the materials were just not there to resist a bending load like that. That is because the materials of choice were basically wood spars and string. When the M-15 was designed, the equivalent materials were aluminum spars and steel cables. Both are excellent in tension, and the spars can also act quite well under compression. So we want to get as much of our wing into tension as possible, followed by compression, and we want to minimise bending loads. Well, here's a way to do it. Just replace the wing with an I-beam. The horizontal members can both be aerofoils. Now, there may be some problems with that. Okay, let's cut out some of the I-beam to make it lighter. That intuitively looks like it'll still hold, so let's cut out some more. In fact, let's replace the diagonals with cables, join everything with pin joints, and we've made a cable truss. And yes, my degree is in civil engineering. I think the only other thing I could have done at this point, more stereotypical, would be to make the thing out of concrete. Honestly, based on what we've discussed so far, I'm surprised the Soviets didn't try that too. Anyway, here's why this truss works in 2 dimensions only, just to keep things simple. Consider this point near the tip of the wing. As the wing tries to flex downwards, it pushes this spar downwards, but this diagonal cable stops the spar from moving by going into tension. That tensile force is transferred into the fuselage as a compressive load in this direction and possibly a tensile load in this direction. Likewise, a lift force on the lower wing puts this member into tension, transferring the load into the fuselage where more material or structure can be added to resist it. So, a biplane doesn't require materials with high bending resistance. It has a shorter wingspan than an equivalent monoplane, but the second aerofoil adds additional lift. Now let's try to decipher what the heck is going on here. Putting the chemical tanks on the wings was certainly a decision that was made, and it completely ruins our biplane model. It ruins a few other aspects too, but we'll get there. Alright, so here's me trying to figure out the load paths. I actually had to rewrite this section twice until I figured out what was happening. I think I was overcomplicating things, and it's probably simpler than I initially assumed. But the crucial detail, I'm pretty sure these tanks were welded to the wings, making the connections fixed. So we can think of this entire box as an extension of the fuselage. It's relatively rigid and contains enough material to resist tensile and compressive loads from the wings. Okay, let's add in the upper wing. This member is a brace for the upper wing. So far, we can consider this setup as a braced high-wing monoplane. There's still a pretty significant cantilever here, so this portion of the wing over the bracing would have to be built to withstand the associated bending load. The bracing itself carries much of the wing's weight as compression and passes it into the fuselage. Now let's add the lower wing. Outboard of the chemical tank, it's independent of the upper wing, so this length is supported entirely by bending resistance here. As the wings are structurally independent, the main structural advantages of a biplane are lost, as there are no cables and wingtip compression spars to effectively convert the bending loads into axial loads. Now finally, we need to consider the maximum of 1.5 tons of payload in each chemical tank. This sits above the landing gear, and I'll give credit here, that's kinda clever if we consider it in isolation. When on the ground, the landing gear takes the load in compression, preventing it being applied as bending to the wing roots. In flight, I'm less sure. For calm conditions, the lift would counter the weight of the tanks. But in turbulence, that heavy load on a moment arm from the fuselage may be trickier to model. The whole thing is a strange hybrid between a braced upper wing and a biplane. I'd summarise it as a widened fuselage braced upper wing with an unbraced lower wing. But it's not quite a torsion box biplane either. So why didn't they do this? I don't really understand. And don't give me extra drag as the answer. This thing already has as much drag as a sail, and the payoff for adding some spars and cables will be less structure in the wing roots, and the wings themselves actually, resulting in a lower angle of attack, offsetting that extra drag. Yeah, it looks ancient, but the Soviets made the biplane bed, so they should have slept in it. Now, I will say, just because I don't fully understand the approach doesn't necessarily make it exclusively bad. But the account written by various contributors years after production ceased does suggest the wing structure was less than optimal. There were no fancy composite materials back then, so all those fixed joints and bending zones needed reinforcing. The empty mass of an M-15 is sometimes quoted online as being 3,090 kilograms. Problem is, that was for the prototype. Structural testing suggested reinforcement was required, so the production aircraft weighed around 3,270 kilograms. The original design predicted just 2,400 kilograms empty mass. The excess was so severe that the Press Control Office forbade the publication of information about the aircraft's empty weight. Yeah. But we still have the absolutely glaring issue of the huge increase in drag imposed by putting 2 chemical tanks in the airflow. In fact, it gets even worse, because those tanks were integral to the structure of the wings, Once they were fitted, they had to stay there. Unlike the AN2 with its removable hopper that could be converted to many other roles, once an M15 was built as a crop duster, it would always be a crop duster. Come hell or high water, I'm pretty convinced those tanks should have been inside the fuselage, as they are on every other crop duster I'm aware of. That would put a higher bending stress on the wing roots, but I reckon we have a lot to work with here. One choice would be to be normal and make the landing gear like this. Could even be reinforced with trusses if necessary. It's fixed after all. Another, and I'm being a bit speculative here, maybe to use the advantage we already have. We have a biplane, so let's use it. I bet it's possible to add a truss or bracing to carry that load out to the gear with a lower drag penalty than putting the tanks as they were. On the plus side, the chemical tanks incorporated an advanced chemical dispersion system. Pressurized air was fed into the top to allow for effective dispersal of the contents, which could be either powdered or liquid. For powder, an auger could also be fitted, and an emergency dump system was present to allow the tanks to be drained quickly by gravity if necessary. The compressed air supply was fed from bleed air from the jet engine, perhaps an actual advantage of using a jet. Although, you know what other type of engine can also provide bleed air for energizing pressurized systems? A turboprop. I have mixed feelings about the fuselage layout for the M15. Some choices appear actually quite smart at first glance, but I think in every case I just find myself asking, why did they do X when they could have done Y? The overall design is best summarised as a short main fuselage which terminates into a twin tail boom. The main fuselage is a semi-monocoque, also known as a stressed skin design, the standard for all metal aircraft since the 1950s. Remember a couple of years ago when some guy claimed to have invented that himself and was calling it an exoskeleton? Ugh. Anyway, let's start at the front and work backwards. Well, here it is. The one part of the M15 that I think looks kinda good. If you crop the rest out, I actually think it looks kinda cute. Now, I've already shown in the past I have absolutely zero taste in vehicle aesthetics, so feel free to disagree with me there. More importantly, the setup was quite practical. One of the design priorities for a crop duster is pilot visibility. Flying low over unfamiliar terrain, pilots need not only to be able to see any hazards on the ground, but also need to be able to constantly orient themselves to ensure even chemical spraying. With the pilot situated at the front and surrounded by an expansive glass canopy, the M15 may provide better visibility than any other crop duster in history. But there's a trade-off. Most crop dusters place the pilot high and in a good vantage point, and they sit behind armoured glass and within a roll cage. That's because crop dusting is risky. One mistake, an undocumented guy line, or a mechanical failure, and your aircraft is potentially on the ground in the blink of an eye. The armoured cockpit is a necessity to protect the pilot in the case of relatively common mishaps. Indeed, the M15 cockpit was armoured with laminated glass, but unlike every other crop duster, there was no engine or major structure between the pilot and the ground in the case of an impact. I will say there's potentially a trade-off here. All that forward structure could crush a pilot in the case of a crash, so it's not necessarily exclusively bad. But the pilot in his glazed cockpit in the nose is reminiscent of a bombardier in a World War II bomber. Vulnerable. Now we move backward to the engine mounting point. This is difficult to evaluate because there's no other single engine jet that's really comparable. Mounting it high would have been pretty much a necessity to prevent debris being ingested during operation on rugged airstrips. Problem is, that engine is mounted really high. It was definitely above both the centre of pressure and the centre of drag. Normally this is undesirable, as increasing thrust would cause the nose to pitch down, exactly the opposite of what a pilot wants when, for example, making an emergency climb. But the report which I use as my main source for this video contains testimonials from a test pilot. To be fair, it's just one opinion, but he praises the handling characteristics of the aircraft and makes no mention of this adverse pitch. It's quite possible there was an interconnect between the throttle and the elevators which automatically nullified it, but I can't find any evidence of that. The first landing did look a little bumpy though, so make your own speculations, I guess. In the testimonial, he also mentions that crop duster pilots will often perform a side slip when coming around for a second pass. That sounds quite dangerous to me, but never mind. It just increases their rate of turn. He mentions that you can't really do that in an M-15 because the aircraft starts vibrating. That sounds rather alarming to me. Now, of course, with all the drag budget used upon those external tanks, the fuselage had to be really narrow. There's only one seat in the cockpit, so I have no idea how pilot training was carried out. Again, this is a bit impractical considering over 10,000 of these were originally intended to be built. I can find no record of a trainer variant, so I'm not sure how the Soviets proposed to train thousands of pilots on something with only a single seat. Seating was provided for 2 passengers in the rear, again limited by the narrow and short fuselage, which also contained the starter engine for the main jet. That short fuselage became the twin tail boom. This was necessary due to the engine configuration. The high-mounted single engine needed a free path for the exhaust, which passed between the tail booms. Now, the only other single-engine civilian jet aircraft I'm aware of that went into major production is the Cirrus CF-50. And that also has a high-mounted engine, but the thrust is vectored slightly downward to take it through the centre of mass and past the single vertical stabiliser. The twin tail boom is actually a bit reminiscent to me of the de Havilland Vampire. I saw one here right next to this AN2. It's simple and reduces overall mass at the expense of a smaller main fuselage and therefore less room for passengers or cargo. But those 2 vertical stabilisers, they just add even more drag. At this point, it's probably apt to reveal there was another crop duster with a remarkably similar airframe to that of the M-15. It certainly didn't share everything with it, but it was a biplane, and it had twin tail booms and a short fuselage on top of tricycle undercarriage. And this one was generally considered pretty good at its job. The Transavia PL-12 air truck was built by a comparatively tiny manufacturer in Australia. 138 were built, so it hardly lit the world alight, but unlike the M-15, those that were built generally lived long lives. Some of them are still flying today, so it gets the honour of being referred to in the present tense. It's certainly not in the same class as the M-15, as it can only carry a maximum of 1 ton of payload. Yet, despite only sporting 300 horsepower, it can still carry more passengers than the M-15. I love an ugly duckling, and I love the air truck. Although it's half the size of the M-15, it's twice the aircraft the M-15 ever was. The M-15 made it into production, which for this channel is the gold standard of success. I have a very low bar, but it fell far short of its predicted demand. In all, 172 flying examples of the M-15 were built, of which 164 were production models. Now that's not a small number. In relative terms, though, it's nothing compared to the thousands that were planned. But let's discuss what could have been. Let's go through the increasingly cursed variants of the M-15. Most were never built, which is probably for the best. A recurring issue with the big heavy biplane was the distance needed for takeoff and landing. So one of the prototypes was fitted with an ejector. Not an ejector seat, a jet exhaust ejector. This is an optimised exhaust designed to increase thrust. And for landing, it was fitted with thrust reversers. These additions were never carried forward into the production version. Again, I do feel that once you're fitting thrust reversers onto your crop duster, it's probably time to take a step backward and ask yourself what you're trying to achieve. This is the polar opposite of helicopters like the Me-2 and the Ka-26, which were actively converted into crop dusters and performed the job with great success. That's despite the higher running costs. The ease of landing and increased mobility made these an economical option. The variant of the M-15 I've shown through most of this video was the first variant, the one with the nice looking cockpit. But the second series removed even that with a more conventional nose. That nose is just screaming for a turboprop to be added to it. There used to be one mounted next to a highway in Hungary, but it seems that was removed recently, which is a shame. The first variant that wasn't actually built but came alarmingly close to it was the water bomber variant. This would have been capable of delivering 2,200 kilograms of water or firefighting chemicals to a target. Would this have been sensible? I don't really know. I just imagine one of the tanks jettisoning and the other jamming shut, which would be not ideal. All built models had seating for 2 occupants in the rear, allowing the M-15 to ferry personnel between locations. The proposed passenger variant would add proper windows and more comfortable seating. For what it's worth, and given what we have to work with here, that doesn't seem like a terrible idea. It may have been possible for pilots to make some additional revenue ferrying passengers between destinations. But why stop in temperate Russia? Why not take this thing to Siberia? I can think of absolutely no reason to do so, but if you wanted to, Mielec proposed the ski version, and then apparently refused to elaborate further. All I have is this low-res drawing of what could have been. Now, you may be thinking, yeah, that's cool, but can we increase the drag even more? How about a float plane version? I'm not sure if the firefighting version was proposed as a float plane. Either way, you would have to convince me hard that this thing could even get off the surface of the water. But the most cursed variant of all, the passenger gondola version. Why not showcase your aviation expertise to the world by designing something that looks like it was designed by a crazy Italian genius in the 1920s? Yes, the passenger version would have replaced those chemical hoppers with 2 passenger cabins. Hell, Mielec even proposed putting a cargo version of that on skis. Many lament the fact that the Soviets only flew Buran once. I'm more sad that we never got to see this piece of childhood artwork fly. Whoa, we're not done here yet. So I found this tiny clip in some Polish archive film showing some more detail of the passenger gondolas. Looks like each one was intended to carry 5 passengers. And it seems the Soviets took the idea home with them. Here's some artwork of the proposed finished product. And here's an actual model of a proposed derivative. And that one has a turboprop. I should be giving credit for that now, but it just looks like an aero, Gavin. And finally, just to dispel a myth, the M-15 wasn't secretly built to drop chemical weapons. Why would it be? It'd do an absolutely terrible job at it. As you will have probably guessed, there isn't really much information readily available on how well the few M-15s that were produced actually performed their job. The test pilot account in the main source for this video speaks very highly of the handling. He mentions an exceptionally tight turning circle on the ground and easy and stable flight characteristics. To be honest, I don't really trust this account. For example, he dismisses shortcomings as, quote, peculiarities, which were not shortcomings for Russia at all, end quote. These shortcomings included a high minimum speed for crop dusting of 110 km an hour, but that was just 20 km an hour below the max permissible speed. And he mentions the long takeoff length, which is really difficult to just dismiss as a peculiarity for a crop duster. Now, let's be fair here. The M-15 did perform well as a crop duster in agricultural trials. And these weren't just made-up Soviet trials. One was assessed in West Germany, at the Chemical Agro Centre in Darmgarten. It could spray chemicals over almost twice as wide a strip of land with each pass and could apparently work at twice the rate of an AN-2. In a vacuum, the M-15 was probably a pretty great crop duster, but it didn't operate in a vacuum. It operated in the Soviet Union. The failure of the aircraft to become widely adopted is, in this report, attributed almost exclusively to external factors. The first of which was absolutely abysmal ground support. Remember, at this point the Soviet Union was falling apart. For instance, chemicals were frequently stored in heaps outdoors where they'd clump together and block the chemical system on the aircraft if not crushed with a tractor first. Of course, I find it difficult to believe that the design of the M-15 wasn't the real reason for its failure. Though one external factor that definitely did curtail production was the global economy. With lower refining costs, jet fuel is more sensitive to crude oil prices than avgas or even gasoline. Now imagine if, say, the oil price tripled overnight, because that is what happened in 1973, and it never really came down again. The refining and transport costs for fuel were basically fixed, so the margin between jet fuel and avgas was reduced. Suddenly, an aircraft which consumed triple the fuel of its piston engine equivalent didn't look so attractive. Finally, I have some actual data to back up not only the failure of the M-15 to compete economically, but also to provide a little insight into its design issues translating into actual problems in the air. I found registration records for 151 of the 164 flying M-15s. Here they are plotted out. Each line shows the date an aircraft left the factory and was subsequently retired. You'll note all of them were retired within 5 years. In fact, many were required on the same dates. Clearly they were part of a production run and all had a fixed time period before some kind of inspection or recertification was required. It appears not a single M-15 was carried past this 5-year-ish recertification. It's probably fair to assume many of them stopped flying well before it. A strong suggestion of an uneconomical aircraft. But we also gain a little insight into operational issues. Now, we cannot compare the accident rate to other crop dusters. If you search for any crop duster type on the Aviation Safety Database, you'll retrieve an alarmingly high number of accidents. That's because crop dusting's dangerous. What we'd really need is the accident rate per hour flown, but that's info I don't have. So instead, let's look at what caused some of the accidents. And by the way, this is the last source I discovered for this video. I wrote this section after the rest of the script, so let's see if this matches up with all the issues I pointed out earlier. One fatality was caused by a pilot forgetting to extend the flaps on takeoff, hesitating, and running out of field and crashing. Pilot error is obviously the major cause here, but the long takeoff distance of the M-15 is certainly a contributory factor. 7 of the aircraft had recorded forced landings. Remember, any of these numbers could be higher, we don't have a full picture here. Some of those were due to electrical failures. One was due to chemicals being ingested into the jet engine. I briefly did mention debris ingestion earlier, though I was more thinking of gravel and dirt, and not bits of the aircraft itself. Because indeed, another M-15 had a major incident due to a screw falling off the windshield wiper and being ingested into the engine in flight. Another one had a design-derived incident I'd not even remotely predicted. It was parked on an incline. Fuel spilled out of the overwing tank and ignited as it flowed into the still-hot engine, causing fire damage. One had a chemical tank hatch open in flight, presumably causing a rapid jettison of that one tank. This made the aircraft uncontrollable, causing a crash which severely injured the pilot. That's pretty much identical to the concern I had with the M-15 as a water bomber. One was scrapped due to an unknown accident, and another is suspected to have crashed during delivery from the factory, which sounds quite funny, but I'm not sure. There's a good chance someone died there. A couple more interesting points. At least 8 of them were retired due to corrosion, which is something the M-15 was designed to be resistant to. And 2 are actually stated as being improved 2-seater versions, which suggests that trainer variant I was wishing for may have been built after all. As I said, it's difficult to draw conclusions regarding accident rate compared to other crop dusters, but it's interesting to see not only the high oil price affect the lifespan so drastically, but also to see direct effects of the very obvious design flaws in the little accident data I could find. And all that, by the way, is why the M-15s apparently all just disappeared, which is the source for the incorrect chemical warfare theory. The last one flew 37 years ago. Apart from the static ones in museums, they're long gone. Many AN-2s, on the other hand, still remain in service. Some of them are still even used for crop dusting. At the end of the day, if you want a crop duster, I think it's best just to build a crop duster, not an amalgamation of several other aircraft types. After all, the AN-2 was never intended to be a crop duster. It just happened to fulfill that role very well. And by the late 1970s, that's what the engineers at Mielec did. And they did so as part of another partnership, but this time not with the Soviets. It was with the Americans. 20 years prior, an American engineer, Leyland Snow, had designed one of the most successful crop dusters of all time, the Thrush. His company had subsequently been bought up by Rockwell, who were interested in upgrading the Thrush with the Polish-built PZL 3 radial engine, itself a variant of the Soviet AI-26. For their part, the Poles took some of the best aspects of the Thrush and increased the payload through various modifications. The result was the M-18 Dromedar, one of the most successful Polish aircraft in history. Many of them are still in active use. Dromedar, dromedary camel, that's what it's named after, because it looks a bit like a camel. Though it's not the giant crop duster the Soviets initially envisioned, it does exactly what it was designed to do. But let's go back to that proposal for a giant crop duster with a 20-metre wingspan and a turboprop engine that kicked off this saga in the first place. It turns out it was built in the end. Just it wasn't built in Poland. It was built in the US. Snow quit Rockwell in the late 1970s to establish his own company, Air Tractor. They initially built reasonably conventional agricultural aircraft with radial engines, but by the 1980s, they started experimenting with turboprops. In 1990, the Air Tractor 802 first flew, with a wingspan just shy of 20 metres and a payload capacity of 4,000 kilograms. It's by most definitions the largest single-engine turboprop flying today, and it almost certainly either meets or exceeds all the original specifications Mielec set out when they began work on the M-14. It even approaches the legendary versatility of the AN-2. It's used as a water bomber, and there's a military variant, the Skywarden, which exploits the high power and armoured cockpit. The Air Tractor is the quintessential rugged agricultural aircraft today. Poland were extremely close to building it themselves back in the early 1970s, but unfortunately the Soviets got involved and we got the M-15 instead. Maybe they should have just used a turboprop. Well, I thought I'd add a bit of a thank you at the end of this, with it being my 100k special and everything. Here's my plaque. Cool, nobody cares. I definitely didn't mount that on the wall the second it arrived. Yes, I never set out to get 100k subscribers. I never set out to be a YouTuber, as my friends have started calling me, but I guess I am now. So thank you massively to everyone who's watched or interacted with, liked, whatever, any of my videos. And obviously, an additional thank you to everyone over on Patreon who continues to support this channel. I think Artem, who does the incredible 3D animations for my videos, deserves a special shout out, and I'd like you to go check out his channel if you have the time as well. There's sometimes some hints for future videos and bits and pieces that are left out from my videos on his channel, so well worth checking out. I've made a kind of tricky decision for me to open a Bluesky account. There's a lot that I'd like to talk about, kind of where I'm going with this channel in the future. By the way, nothing's going to change, but just, future topics, that kind of thing. And I think the YouTube community page isn't quite enough. So for anyone interested, it's live now. I'll put the link probably on screen somewhere. You can go check it out if you want. Now, there's a few kind of criticisms I get every now and then in the comments. Most of them are honestly quite positive. Constructive feedback is, I believe, the term. I'll address those over on Bluesky as well. We don't need to go into all of that now. But yeah, in short, I'm going to continue with approximately the same release schedule I have now. Same types of videos, hopefully improving quality over time still. And yeah, I hope to see you around in the next one. I'm keeping the topic for that one secret, I'm afraid. But I can say this will be the last time the hideous wallpaper is going to appear in any of my videos. It will be redecorated the next time you see it, and it will be topic appropriate for the video it's in. So I'll see you there, and thanks again.